unmuted? Yes. Okay. Sorry. All right. So next up, we have Basil Saeed from Stanford, and he's going to talk about the local minima of empirical risk in high dimensions. Thanks.
Okay. Okay, I'm going to start. First, let me acknowledge that this is a joint work with Ken Asghari and Andrea Montanari. I want to say that this is a theory talk, so there's going to be a few I can't really show you anything without showing you a few equations. But you know, the equations that are complicated and are not necessary for you to understand, I've grayed out. So if you're not an expert, you can just gloss over them. I'll say a little bit more about them. But okay, I'm kind of glad that we switched because Philippe already introduced the model that I'm interested in. I'm also assuming that I have IID samples, xi, yi, and that xi, well, in my case, I'm going to take xi to be IID samples from a Gaussian distribution in RD. And the yi is also a multi-index model generated by by taking k-dimensional projections of this xi. Once again, I'm going to take, I'm really not getting used to this guy. And so theta is going to be a d by k matrix, and each yi depends on xi only through k-dimensional projections. Okay? And like before, wi is going to be my noise parameter. I'm going to be interested in empirical risk minimization. I'll say exactly what. But this is the standard empirical risk problem where I have some loss, some featurization map, and some regularization. And I'm going to be trying to say something about the local minimizers of this empirical risk. Okay? And I'm going to use theta hat to denote a local minimizer. Okay, I won't get into specifics which one, but it'll be clear. Okay? From the mathematical point of view, I can replace L, F, and this yi into this formulation so that now I only can have to say things about this L, just mathematically. And so now all my assumptions are just going to be in terms of L. The full assumptions are in the paper, so I won't get into the details. But essentially what I need is the regularity of L, some tail conditions on my noise distribution P, and I need some kind of well-behavedness on my true theta 0, my ground truth theta 0. Okay, good so far? Okay. I'm also going to be working in this high-dimensional regime where n and d, so the number of samples and the dimension of the indices, goes to infinity, while n and d remain fixed at a ratio alpha. N over d converges to alpha, where alpha is in 1 to infinity. And I'm going to be interested in trying to say something about these theta hat. So this is a talk about high-dimensional asymptotics of this, if you know what that is. And once again, I'm going to keep the number of indices and the dimension of y fixed, order 1, with respect to n. Okay? So you might be familiar with other tools that do this kind of stuff, like AMP or Gordon, or so there's some more specialized stuff. But if you're familiar with these, you also know that they have limitations. And unfortunately, I don't have time to go into the limitations if you're not an expert, but you can ask me afterwards, and we can talk about it. I also won't tell you why this method is better, maybe, but this is going to be a new tool along the same kinds of lines, or a new approach, okay? Maybe not new, but an approach. Okay? Okay, don't want to oversell. But I want to say a few things about high-dimensional asymptotics for the non-experts, though. So suppose that you're an analyst and you're interested in studying a specific setting. Okay, you have a loss, you have some distribution on the noise, etc., and you're interested in, say, quantifying the training error. It behaves in some way, and you want to see how it behaves. Okay, you can look at what you're really interested in is you're interested in quantities like this, the training error, which is effectively just the empirical risk evaluated at a given theta hat, right? Or your estimation error, just the L2 distance between theta hat and theta 0. But you're interested in these for fixed n and d. For fixed n and d with n over d at a fixed alpha. Now this theta hat is a function of x. It's some horrible object, right? And it's certainly dependent on xi. So even if you know how to compute this guy, now there's some horrible dependencies here. But the nice thing is, as n and d go to infinity, this concentrates. Right? These quantities concentrate to some deterministic limit often. Okay? So the hope is that if we design tools that we can estimate, we can analyze these quantities, the asymptotic quantities, for a sufficiently large n and d, we can say something about we can try to understand the behavior of these random quantities if they're close enough to their, okay, they concentrate, they are. Okay? Is that clear? Okay. Just to streamline what I want to do, I want to define these two quantities. So for a given vector theta, d by k, this is the same space as my parameter where I'm optimizing over. I'm going to define these two empirical distributions. So given theta, I get a distribution. The first distribution, what am I doing? For every sample I, I'm going to project xi onto theta. It's a k-dimensional vector. I project xi onto theta 0. I get a k-dimensional vector. And then I concatenate the noise. Okay? And for each I obtain a vector. And I use these vectors to form an empirical distribution. Okay? And this, I'm just taking theta, theta 0, taking the rows, using that as an empirical distribution. Don't worry about the normalization. Okay? And the point of this is it's nothing magical. It's just that now I can rewrite quantities like that as expectations under these empirical distributions, just functionals of these empirical distributions. Okay? So this is just a notational thing. Where these empirical distributions are now evaluated at a given theta hat. Okay? So now I can just state the goal a little bit more clearly of what I want to do. Okay? Now I want to find the limits of the probability of mu hat and mu hat evaluated at theta hat. Okay? They're random measures. That's why it's a limit in probability. Okay? And what kind of limit, we won't get into it. Okay? And of course in these asymptotics. Good? Okay. So I'll just give you a high-level idea of the approach. I won't get into details of the proof, but it's just really technical. And for intuition, let me assume that r hat n of theta is strongly convex. Okay? Is beta strongly convex? Given some set A and B, so remember that mu hat lives in this space and nu hat lives in this space. Okay? So given some set A and B, I want to ask what is the probability that mu hat and nu hat are not in A and B. I want to upper bound this. This quantity I can write as the probability of this set being empty. What is this set? This is the collection of theta that are critical points of my empirical risk, where the empirical risk is strongly convex. Okay? While mu hat of theta and nu hat of theta are outside of A and B. I'm sorry? So right now, I'm assuming beta is strongly convex. Okay? I'll say more later. I'm assuming beta is strongly convex so that this is exactly, there's only one in this case, right? Now, this is what? This is an expectation of the indicator that there's at least one element in this set. And this is, of course, bounded by the number of elements in this, by expectation of the number of elements in this set. Right? And maybe you recognize this if you worked on stuff like this, that this is just the expectation of the number of zeros of some process. Some random process, and luckily we have a beautiful tool for this called the Katzreis integral, where given a generic regular random process, you can compute the expected number of zeros of the process when the indices are constrained to lie in some set S. Okay? And there's this integral formula that's grayed out, so you don't have to read it. Okay, this was known since like 1940s, I think, or something like that. Okay? And essentially, this is what, you can take this, compare this formula to this formula, and try to match the terms. Theta gets replaced by t. The gradient gets replaced by g, and this set gets replaced by this. Okay, this is a lie because it's a random set, but essentially, I'm going to use something like this as my constraint set. Okay? So the first theorem is going to be about computing the asymptotics of this using exactly this kind of approach. So you crank, and you get this, which is exactly just the upper bound that I showed you. Okay, maybe I'll just say that. Okay, this is the term that you just saw before, and it's upper bounded by something. Why is this nice? Because now if you look at just what we did when we asked, what is the probability that mu hat and nu hat are not in some set A and B, complement by the Markov inequality that we did before, plus this theorem, we get something like e to the minus n times inf of star of phi of mu nu star. That's exactly what this theorem says, plus little o of n. And I'm only able to bound it on a high probability set, omega n, so this I get an omega n complement. Okay? So this gives me a way to try to get tail bounds on the probability that mu hat and nu hat are outside this set. Of course, this is kind of useless unless I know something about this quantity. Okay? But luckily, the theorem gives me an explicit formula for what phi star and mu star are, which I'll show you in a second to not scare you, because they're not important. But it gives me some formula, and so I can try to analyze them. I'll tell you at the end. I can tell you at the end. Okay. Maybe I'll say that there's a big asterisk to answer Marco's question, for instance. So this is not exactly the same set as before. There's additional constraints on what theta has to satisfy, but you can think of this set as a collection of theta that we can actually say something about. Okay? Naturally, you're not going to be able to say something about theta where the gradient is equal to 0 using something like this, but so I can take, I can take this to be e to the little o of n. Okay? And just the formulas for 10 seconds. Okay. Okay. All right. So like I said now, okay, maybe I'll mention that, these kinds of asymptotics, this kind of thing was analyzed in a previous paper by Antoine Millard and Benarous, but it was a much simpler ARM formulation, and it was done without analysis of this phi star that I'm going to tell you in a second. And I think for a different dogma. Okay. So I'm going to restrict now to the convex case and try to lower bound this phi star that I just mentioned. So this theorem states that, first of all, for any mu and nu in this set of S star that are feasible, I can ensure you that phi is bigger than or equal to 0. But that's not enough to obtain a bound. But I can also say that equality with 0 only holds if and only if mu and nu satisfy some collection of fixed point equations. What are the fixed point equations? If you've worked on AMP and such things, you can recognize these kinds of equations. The important thing to know is that despite these characterizing an infinite dimensional object, these are fixed point equations in order k-squared many parameters. Given R and S, I define mu and nu explicitly. Given mu and nu, these tell you how mu and nu have to be related with R and S. Okay. But now the question is, is there even a solution to these? And you have conditions under which there exists a unique solution for these. For instance, if lambda is bigger than 0, the solution exists and is unique, as you'd expect. If these characterize your minimizers, you'd hope that when your problem is strongly convex, you have a unique solution. And if lambda is equal to 0 and L is strictly convex, then you can either have a situation where there exists a unique solution or there's no solution at all, like logistic regression, like we saw yesterday when Jing Feng was talking. Okay, just to maybe hammer it down in case it's not clear. So so what does phi look like now? If I plot phi against the space of mu nu, it looks something like this in the convex case. And it's exactly equal to 0 at some mu star, nu star, that satisfy these fixed point equations. So now I can continue my analysis here. If I take A to be, let's say, the Wasserstein 2 ball, it's a ball in the space of measures around mu star with radius epsilon, and my B, same thing, but with nu star, this allows me to conclude that nu hat, for this A and B, the probability that they're outside A and B is upper bounded by this. Well, outside of this phi is bigger than 0, so I get an exponential tail bound, allowing me to conclude that mu hat converges in Wasserstein 2 distance to mu star, and nu hat converges to nu star. Okay. I have an example, but there's no way I'm going to go through it. But you can plot it, and it's solvable is the point. Okay. Sorry.
You have like a minute to finish.
Oh, do I? But okay, there's nothing I can go over at this point. But okay, I mean, this is one example that we did, the multinomial regression. and maybe just think of it as a way to use this. I mean, you're given some data, you start out with a given distribution of your yi's, and you have a given loss function. You can compute exactly what the fixed point equations are, and using these fixed point equations, you can solve for R and S, and find what mu hat and nu hat are, and estimate whatever quantity you want that's linear functional of mu hat and nu hat. I have nothing else.
Thank you very much.
Sorry, maybe.